Hi friends, welcome back to yet another video. Here in this video we are trying to solve a very important problem from the field of solid mechanics. There is a technique called auto frottage. Some of you may have heard of it. It's a metalworking process actually used for fabrication or used in the fabrication of tubings that will undergo very high internal pressure. Okay, so the process goes something like this. You will have two tubes like as shown in this figure, and let's think of a scenario where your R2 is greater than your R3. So this is the outside ring and R2 is the outside dimension or the outside diameter of the inner ring. Let's think of a scenario where R2 is greater than R3. Then you can't simply fit this inner ring A, inside the outer ring B. You can't simply fit in. So what you will do, you will heat this outer ring and then try to fit it over the inner ring A. Make sense? Since it is at a higher temperature, this will undergo thermal expansion and it will be rather easy for you to fit this outer ring over this inner ring. Now what happens when both rings come back to its original temperature? It will shrink, right? It will shrink, or the dimensions will reduce. Initially the dimensions of this outer ring when it was heated will be larger compared to its dimensions at the room temperature. Make sense? Now what happens? There will be some kind of a pressure distribution generated in between this interface. Make sense? This radius will no longer be R2. Okay? This would have reduced. Make sense? And this radius will depend upon a lot of things, the dimensions, the material properties, and a lot of these things. So this is the whole introduction to the problem. So auto frottage is a mechanical working operation which we usually do. Now in this particular problem they are asking us to compute the pressure between the two rings when ring B reaches the temperature of inner ring. Okay, so that was a lot of introduction. As I usually say, try to solve the problem on your own. If you are not able to do that, come back and see rest of my video. So apologies for my poor sketch, but again as shown over here, this is the inner ring and this is the outer ring. This is the new radius. I'm calling it R underscore int, R subscript int, to just to mention that that is the interface radius. Okay, now what should be our next step? I told you there will be some kind of internal pressure over here, like you can say the contact pressure or whatever. Then in this segment I'm trying to draw the Freebody diagram for the inner ring as well as the outer ring. Now if you look at the inner ring Freebody diagram, it is acted upon by a pressure. Let's call that pressure PC. It's a contact pressure. And for the outside cylinder, this acts as an internal pressure as shown over here. So for the outer ring it is acting as an internal pressure, and for the internal ring it is acting as an external pressure. So now you should apply your logic. What should actually happen to each of these systems? What should happen for the internal ring and what should happen for the external ring? So okay, I will come back to this formula kind of stuff after a while, but for the time being, let's see what should happen. See, the inner ring should shrink by R2 minus R int, right? So this inner ring, because of the external contact pressure, sorry, I will use a different color. Because of the external contact pressure that is acting on this ring, it should shrink. It should shrink by an amount R2 minus R int. Similarly, using the same logic, this external thing is acted upon by an internal force like this. Both are same because of Newton's third law. The contact pressure should be the same on either rings. Now the outer ring should elongate by R int minus R3. Okay, R int is a value which lies between your R2 and R3. Okay, makes sense? Now, in order to do this problem, you should be in a position to connect this external pressure to the radial deformation that is happening in the ring. Clear? You should be in a position to connect the radial deformation of the ring with the external pressure that is acting on the ring. Make sense? No big deal. How to go about doing that? Oh, let's stick back to our basics. So I know that in this condition there will be only hoop stress because these are simply two rings. There are no closed ends, so there is no scope for longitudinal stress to come into the picture. So I have a hoop stress scenario. There is a single stress acting on the ring, that is the hoop stress, and it is given by this particular expression shown over here. Okay, very simple. Now let me pay a little bit of attention to the deformed shape. Let's say this was the undeformed configuration. Undeformed configuration is this. What happens when there is internal pressure acting on the structure? Let it be external or internal. For the sake of explanation, in this scenario I am expecting or I am assuming there is an internal pressure acting on the system. So what happens? This undeformed ring will try to expand. Am I right? And this is the deformed configuration. The solid line represents the deformed configuration while the dotted line represents the undeformed configuration. Now from this it is clearly evident that the perimeter of this particular circle is more compared to the perimeter of this particular inner circle which corresponds to the undeformed configuration. Clear? So in effect there is a change in length in the hoop direction. There is a change in length in the hoop direction. Okay, there is a change in length. Now you want to connect this change in length with respect to the internal pressure that is acting on the system. Now we need to resort to our strain stress relations as shown over here. So I know there is a change in the hoop direction, there is a change in length in the hoop direction. So I'm trying to compute what is my hoop strain that is coming in the ring. It is given by Hooke's law as shown over here, sigma theta by E, where E is the Young's modulus, minus mu is the Poisson's ratio, times sigma L, which is the longitudinal stress, divided by Young's modulus. In this scenario, there is no longitudinal stress, so simply this term drops off. So we are left with only this particular term. So this is my epsilon theta. Now, using the aforesaid concept, what will be my epsilon theta? Strains are simply given as change in length as a ratio of change in length to the original length, right? Now in this case, the change in length can be written like this. Make sense? This is the perimeter corresponding to the deformed configuration, and this is the perimeter corresponding to the undeformed configuration, and this was the original length. This is a very important relation. This you can make use of very regularly when you do structural simulations of cylindrical objects. What is the radial, see this radial movement, see this particular ring has moved radially by this amount dr. It is related to the hoop strain, which is in turn related to the hoop stress, and this hoop stress is a function of your internal pressure. Once again, as you apply an internal pressure, there is a radial outward movement for the structure, which is given by dr. It is connected to your hoop strain, which is connected to your hoop stress, and your hoop stress is connected to the internal pressure. Make sense? Now rest of the things are simply plug and chug. Now this expression gives you, for a given internal pressure, Young's modulus and thickness of the ring, what is the delta radial movement that my ring will have. Make sense? Clear? Okay. Now, having seen this formula and having seen the utility of this particular formula, now we can go ahead and use this formula to solve our problem, because conceptually we have put everything into buckets. Now it's just a matter of clubbing them. We know physically the inner ring should shrink by R2 minus R int. Now we should translate that physical statement into a mathematical statement. That's what I am trying to do over here. See, it is the radial deformation in the inner ring should be R2 minus R int, then equal to P is the contact pressure, R1 square is the radius. Since this is a thin ring, we can interchangeably use either R1 or R2, but in this case I am using R1, P R1 square divided by TE, where T is the thickness. Now thickness can be substituted as R2 minus R1. Make sense? No big deal. You have an inner radius, you have an outer radius, so the thickness will be essentially the difference in the radii. Okay? Now going ahead, going with the same logic, the outer ring should elongate by Rn minus R3. What does that mean? Rn minus R3 equal to P R3 square. Okay, because for the outer ring, the initial dimensions were R3 and R4. Okay. Now R3 square divided by TE. T can be again substituted as R4 minus R3 by the same logic used for the inner ring. So now we have these two very beautiful equations. What we are asked to compute? We are asked to compute what is the contact pressure in terms of all the non-quantities. See, R int, this internal radius is not a non-quantity. All other dimensions are not, because they are all dimensions pertaining to the structure or pertaining to these two rings, which are non in advance. R1, R2, R3, R4 are non in advance. Now, just have a glance at these two equations and think of yourself how we can get P, which is the contact pressure. Very simple. Now you can add these two equations together. Once you add these two equations together, what happens? Once you add these two equations together, R int will get cancelled because there is a minus and here is a plus. So R2 minus R3 can be written as, once you add these two equations together, it can be written as like this. R2 minus R3 will be P divided by E, and this slightly long function of R1, R2, R3 and R4. It's simply a plug and chug. It's plug and chug from now onwards. From this expression you can solve for the contact pressure. P equal to E into R2 minus R3. All these things can be done. Just a quick check, you can check for the dimensions when you solve for these really complicated when you have a complicated expression for the internal pressure, just to make sure that you have got it correct, you can check the dimensions like this. See, here we will be in the denominator, the dimensions will be the length, the dimensions of length, and here we have dimensions of length times dimensions of E, Young's modulus. So pressure and Young's modulus share the same dimensions, so this makes sense. Make sure. Thanks for watching. Hope to see you in the next video with another interesting problem.